So up to now we've seen how we can solve an optimization problem in discrete time. So for simple problems we can use the method of Lagrange or the method of Kuhn-Tucker. And if the problem is of low dimensionality and so on. But in general we would use the method of Hamilton-Jacobi-Bellman. Now we move on to the situation of continuous time, and solving optimization problems in continuous time can be done by optimal control theory that goes back to Pontryagin. And this is what we do next, so it's the most convenient way of solving dynamic optimization problems in continuous time. As we will see, the mathematical methods of this procedure are rather different to discrete time. Again, the reason is that we cannot differentiate with respect to time in discrete time, but in continuous time we can take the derivative of a function with respect to time, and therefore we will deal with differential equations and integrals over time and so on and so forth, all what we can do when the functions that we deal with are continuous. However, what we will also see in the end is, although the methods differ quite a lot, the result is remarkably similar. So we will also get a consumption-Euler equation in the end for the particular example of utility maximization by choosing an optimal sequence of consumption over time, or an optimal path actually in this case. And the interpretation of the consumption-Euler equation in continuous time will be basically exactly the same as in discrete time, but the formulation is in the terms of a differential equation. Now, optimal control theory goes back to calculating the optimal thrust of a rocket that should bring a payload into Earth's orbit. So it goes back to the 1960s actually and 1950s. Where the problem was actually to set the control variable, which is the thrust of a rocket, and this is a continuous this is something that happens continuously, basically. So time evolves continuously, so I want to know the optimal thrust at each moment in time, given the payload that I have to bring into the Earth orbit. And the state variable of the whole thing is the velocity of the rocket. And by adjusting thrust, I can change velocity. And interestingly, most economic problems in terms of consumption savings decisions have lots of similarities with the problem of setting optimal thrust to a rocket that has to bring a payload to Earth's orbit. And we will also see, for example, that one of the side constraints, the transversality condition, is also has a similar interpretation. So in bringing a payload to the Earth's orbit, you have to ensure that the payload at the end, when it arrives in the orbit, has exactly the speed at which gravitational forces and centrifugal forces balance each other off, such that the payload circles around the Earth. So this is exactly one speed that manages to do this. If the speed were higher, then the payload would basically circle out into space. So the centrifugal forces would be higher than the gravitational forces. And if the speed is too low, then the gravitational forces would be higher, and therefore the payload would in the long run fall back to Earth. And it's the same somehow with consumption savings decisions when we have an endpoint condition, and the endpoint is basically when either the individual who maximizes or the aggregate economy, if the one who maximizes is a dynasty or the head of the dynasty, dies. Because in this case, what one would want to have is no assets left over. Because if I had assets left over at the point when I die, I could have increased lifetime utility by consuming more. And this dynamic constraint, we will see later on, that's the transversality condition, gives us an endpoint condition that, together with the initial condition on the capital stock, is able to determine or to provide restrictions on our system of two differential equations that results from applying optimal control theory, such that we can determine the particular solution to the system of differential equations, and not only the general solution, as we will see later on. Now again, consider an average household, and the household inelastically supplies 1 unit of labor on the labor market and earns the going wage W as previously. Now the households again decide to split how much to consume and how much to save. So the trade-off is again between increasing utility today by consuming more, but in exchange foregoing interest income for consumption in the future. And I have to balance these two aspects off, and therefore we look for an optimal path of consumption and therefore an optimal path of savings over time and of capital accumulation. And so we will get a system of two differential equations, the evolution of consumption and the evolution of assets over time, that we want to solve for the general solution and the particular solution later on. So again, what a household would do is to sum up all the instantaneous utilities that are generated by consuming a certain amount CT, and we would sum this up for all instances between the beginning of the decision period at time 0 and the end of the planning horizon at time uppercase T. Now in continuous time, it's not a sum that we have here, but an integral, because we can integrate over time utilities. And in the following, we will follow the convention in the literature and suppress the time index T whenever this can be safely done without impairing the clarity of the exposition, because we save a lot of notation in doing so. Now again, usually we assume infinite planning horizons such that uppercase T goes to infinity. This simplifies the problem quite a lot. We don't have to consider scrapping values and all that kind of stuff. And it can be justified again by assuming that not an individual makes optimal decisions for herself, but a head of a dynasty makes optimal decisions on behalf of the dynasty. So you also consider your children, grandchildren, and so on and so forth, such that the planning horizon becomes infinite. Well, also in continuous time, households discount the future. The discount rate is rho, such that, analogously to the discussion of differential equations, the discount factor is e to the power of minus rho times t, the time. And the lifetime utility is then the integral from time 0 to infinity, the end of the planning horizon, of the instantaneous utilities, multiplied by the discount factor and integrated over time. Now households own assets denoted by A. Interest income is again, so the interest rate is R, and interest income paid on assets is R times A. Households earn labor income, W. We normalize labor input, which is exogenous to 1. And in such a setting, the assets of households evolve over time according to the differential equation here. So we have the derivative of A with respect to time. That's the evolution of A, so the change in A at a certain instant is given by interest income on past assets, R times A, plus wage income minus consumption. So this is total income consisting of wage income and asset income. And if we subtract consumption expenditures, then we have savings basically here. And these could be positive. If it is positive, the right-hand side, the derivative of A with respect to time is positive. So assets accumulate, the change in A is positive. But if consumption is very high and exceeds wage income and capital income, the right-hand side is negative and A decumulates, A decreases over time, and we have capital decumulation basically. Households dissave. And this is now called the flow budget constraint in this setting. As I said before, there is another side constraint actually. And that's kind of an endpoint condition, the transversality condition. And this consists of two parts. One part is the so-called no Bonzi game condition that ensures that households do not go ever more into debt to finance higher levels of consumption. So if the time horizon ends at uppercase T, which could also be infinity, then the level of debt must be non-negative at that point, because otherwise financial markets would not allow such a solution. So basically in the last period, if you will, the amount of assets has to be non-negative. In case of an infinite planning horizon, the equivalent formulation is that the limit as time goes to infinity of assets at time t multiplied by the discount factor over the whole time span must be non-negative, where the discount rate over the whole time span is the average interest rate given by 1 over t, and the integral over all interest rates from time 0 to time t integrated over tau, basically. So that's the average interest rate. So that means one interpretation is that that can only grow at a rate that is lower than the average interest rate. So in this case, households would basically pay back debt if they have debt and do not accumulate even more debt. To put it differently, you are not allowed to borrow and pay back the borrowed money with even higher debt. And in more compact formulation, it means that the present value of assets must be non-negative. And that's basically the no Bonzi game condition. It rules out a Bonzi scheme where somebody just pays back her debt by going to the bank, asking for an even higher loan and paying back the previous loan, but basically indebting herself indefinitely, which the financial market would not allow for. Now, the no Bonzi game condition itself, however, only states that the net present value of assets limit must be non-negative. It does not say anything whether it could be in principle positive. However, we all know from considerations of optimality that if the planning horizon ends at some point and we have positive assets, then this is basically something that is not optimal, because everything ends, assets are scrapped in the end, and we could have increased utility over the lifetime horizon by having fewer assets at the end of the planning horizon and therefore allowing for higher consumption during the lifespan, basically. So only a level of assets in the final period that is equal to 0 is consistent with optimal behavior, basically. And again, the equivalent formulation for an infinite planning horizon is that the limit as the amount of assets multiplied by the discount factor as time goes to infinity has to be equal to 0. So that's basically the transversality condition, that it encompasses the no Bonzi game condition, so it does not allow to be this term to be negative, so that's the no Bonzi game part, but it can also not be positive because that wouldn't be optimal. So only a solution path for which it holds that the limit as time goes to infinity of assets multiplied by the discount factor is equal to 0 is consistent with optimal behavior. And that's again analogous to the problem of shooting some payload into Earth's orbit, where the final speed of the payload has to be exactly as high so that the gravitational forces and the centrifugal forces balance each other off. And basically that's the condition ensuring that. And now we have all the ingredients to solve the optimization problem by means of Pontryagins maximum principle, which is what we will do next. So first we state the problem in general terms without a specific reference to an economic application, but later on we will use the framework to solve for a standard consumption savings problem. So now we let again denote x the state variables, which would be in case of this example of a rocket the velocity of the rocket, or in case of a consumption savings problem assets of the household. And c is the control variable in the problem of maximizing utility by choosing optimal consumption and savings. That would be consumption. In case of the payload that has to be sent to the Earth's orbit, that would be thrust of the rocket. Then f of t, x, and c in general terms will be the objective function. So in case of the problem of maximizing utility, that's discounted utility, which is what I want to maximize. It could be also the payload of the rocket or something else. And g of t, x, c is the general formulation of the dynamic constraint, for example, the flow budget constraint or certain natural laws governing velocity. Then we write down the problem statement where we maximize lifetime utility, or the objective function basically, from time 0 to uppercase t, subject to the dynamic constraint where the derivative of the state variable with respect to time is equal to the dynamic constraint, g, t, x, c. And we have an initial condition for the state variable. And we have, of course, that the state variable has to fulfill the transversality condition. So then the problem is posed. We also allow for an infinite planning horizon, and we can now state, again in a terms of Cookbook procedure, how we can derive the optimal choice of the control variable for such a problem, which we do next in general terms, and afterwards we will go to the specific example of maximizing utility by choosing an optimal consumption path. Now, how do we solve such a dynamic optimization problem? The first step is to define the Hamiltonian, and the Hamiltonian is the objective function plus the co-state variable, which is kind of related to the Lagrange multiplier in discrete time or in a static optimization problem, but basically we would have a co-state variable at each moment in time multiplied by the dynamic constraint. So that's the Hamiltonian. In the second step, we have to derive the necessary first order conditions for an interior maximum, for which the control variable and the state variable fulfill the following conditions. We take the derivative of the Hamiltonian with respect to the control variable and set this equal to 0. That's a standard first order condition, ensuring that we could not increase the Hamiltonian anymore by changing the control variable at a certain point in time. Only then the choice of the control variable could have been optimal in the first place. So that's intuitive. The second equation is the derivative of the Hamiltonian with respect to the co-state variable, lambda, and that again gives us the dynamic constraint. So the evolution of the state variable over time. So that's again the constraint. And of course, for an optimal solution, the constraint has to be fulfilled. For any solution, basically, the constraint has to be fulfilled. So that's what we would also have to some extent in static optimization. But the third condition is not something that we are familiar with. It's related to the evolution of the co-state variable over time. And basically it states that the derivative of the Hamiltonian with respect to the state variable has to be equal to the negative of the evolution of the co-state variable. And the economic interpretation for that, or the interpretation for that in general, is that if the state variable increases, then the shadow value of the state variable would decrease, and the rate of decrease has to be equal to the amount by which the Hamiltonian increases when the state variable increases. So I think the most accessible interpretation of that is in terms of the consumption savings problem, where the state variable is assets. Now, if assets increase, that means that I can buy more consumption in the future, which would mean that the Hamiltonian increases. And for the optimal increase in assets over time, the shadow value of assets must decrease basically by the same amount as the increase in the Hamiltonian is. That means if I get more assets, I can buy more consumption in the future. That increases my Hamiltonian and my utility basically. But since the utility function tends to be concave, the increase in utility is by less and less, so that the shadow value of assets decreases. And only if the shadow value of assets decreases by the same rate as the Hamiltonian increases for increasing assets, I could not make an intertemporal allocation that would make me better off. Only at that intertemporal allocation I would have an optimum. So these three conditions have to be fulfilled for an interior maximum, and of course the transversality condition also has to hold. That's the second step, and in the third step we need to solve the system of equations that we have here and analyze the dynamics further. So again, this slide just restates the interpretation of the co-state variable lambda. It can be interpreted as the shadow price of the state variable, which is assets in terms of the consumption savings problem. And it's analogous to Lagrangian, but now depending on time, such that lambda is basically a function of time. So we have one restriction actually per instant. Next, we apply this Pontryagins maximum principle, optimal control theory, to the intertemporal maximization problem for the optimal consumption savings decision of households. Now, in this case, what we have is that households want to maximize their lifetime utility, which is the integral from time 0 up to infinity of instantaneous utility multiplied by the discount factor and integrated over time. And they maximize this by choosing an optimal consumption path. So that's the central difference with respect to static optimization. We do not choose just a single number as in static optimization. Instead, we choose a function over time that should be optimal. And households maximize this subject to the flow budget constraint, as stated before, so the derivative of assets with respect to time depends on income minus consumption. So if income consisting of wage income and asset income is higher than consumption expenditures, assets accumulate, so the derivative is positive. If instead consumption expenditures are higher than income in terms of wage income and asset income, then assets decumulate, the right-hand side is negative, and the time derivative of A is negative. Initial assets are given, and the transversality condition has to hold. So the limit as time goes to infinity of the product of assets with the discount factor has to be equal to 0. And the consumer chooses, as I said, the optimal function CT, and the future developments of wages and of the wage rate and the interest rate are assumed to be known to the household. So we assume perfect foresight, as it is often done in economic models. So now we apply the Cookbook procedure we've seen before to this intertemporal optimization problem. And the first step is to set up the Hamiltonian. And the Hamiltonian is the instantaneous utility function multiplied by the discount factor plus the co-state variable multiplied by the constraint. Now, and this is a side remark, this is the formulation of the present value Hamiltonian. In case of the present value Hamiltonian, we have the discount factor in the first term of the Hamiltonian. There is another alternative formulation, the so-called current value Hamiltonian formulation, where the discount factor does not show up here, but instead it shows up in the co-state variable and in the first order condition basically, but to an extent that the final result is equivalent. So irrespective of whether you encounter a present value Hamiltonian formulation or a current value Hamiltonian formulation, the final result should be the same. Sometimes one of the two is easier to apply, and here we just follow the present value formulation. Okay, so then you have the Hamiltonian, that's the first step. Then we take the derivative, we calculate the necessary first order conditions for an interior maximum by taking the derivative first of the Hamiltonian with respect to the control variable consumption and setting it equal to 0. And from this we get this expression here. So we have the derivative of the utility function with respect to consumption, we have the discount factor, and we have minus lambda, the co-state variable, because we have C here with a minus sign. So this is the first necessary first order condition. Then we take the derivative of the Hamiltonian with respect to the co-state variable, and what we get is basically the evolution of assets, namely the constraint W plus RA minus C. So we get the dynamic constraint here from the second first order condition. And the third first order condition we know is that the derivative of the Hamiltonian with respect to assets must be the negative of the evolution of the co-state variable. And from this we get here, if we take the derivative with respect to A, the first part does not depend on assets. Here we have assets only in the second term in the brackets. So we have lambda times R, that's what we have here, and that has to be equal to the negative of the co-state variable. So we see here again by an interpretation, if we reformulate that, we would have that the rate of decrease of the co-state variable has to be equal to the interest rate. And that means that as assets accumulate, and they accumulate, for example, by having asset income, then at the interest rate, then the shadow value of assets would decrease at the same rate. So that means as assets accumulate, the shadow value of these assets at the optimum should decrease at the same rate as the interest rate. And that makes sense, because otherwise, if assets accumulate faster, the shadow value would decrease faster than the interest rate, which would then not be optimal. I could increase overall utility by saving less, such that assets accumulate at a lower rate. And by contrast, if the converse holds true, I could increase lifetime utility by saving more. So therefore, that's the interpretation of the third first-order condition as we had it before, but again in the context of asset accumulation. And we have that the transversality condition has to be fulfilled as always. Now, from the first-order conditions at the previous slide, we basically get a solution system in two dynamic equations, namely the state equation for assets and the co-state equation for lambda. So these two variables appear with their derivative with respect to time. Consumption, the control variable, does not yet appear as a derivative with respect to time. Now, in principle, that wouldn't be a problem because we could also address the solution of the system in the state co-state space from a mathematical point of view, and we could do all the analysis that we want to do. However, from an economic interpretation, basically, we are used to think in terms of the control variable consumption and the state variable assets. So what we want to do now is to transform the system of equations into the control state space. And to be able to do so, we want in the end to have a dynamic equation for consumption. And we want to get rid of the co-state variable lambda. Now, to do this, what we do first is we take the logarithm of the first order condition. If we take the logarithm, what we get is the logarithm of u prime of c minus rho times t times the logarithm of e, which is 1. And we bring lambda to the right hand side, of course, to take the logarithm, and we have on the right hand side the logarithm of lambda. So we have this expression when we take the logarithm. And then we differentiate the result with respect to time, which we know by taking the derivative of the logarithm of a variable, we get the growth rate of the variable. So we have lambda dot over lambda here on the left hand side. And on the right hand side, we have the derivative of the logarithm of u prime of ct with respect to ct. Now this is 1 over what we have in the logarithm, inside the logarithm, so 1 over u prime of c, multiplied by the derivative of u prime of c with respect to time. And here, the second term, if we take the derivative with respect to time, then of course t drops out and we have minus rho. Then, if we take the derivative of the numerator here with respect to time, we know that consumption itself depends on time, so we have to apply the chain rule, which means that we have the second derivative of the function u with respect to c here, and we have the inner derivative of c with respect to time, which is c dot. So then altogether, from the first order condition, from this equation, we get an expression for the growth rate of the state variable in terms of the first and second derivative of the utility function, the rate of impatience of households, and the time derivative of consumption. And now we can use the third equation, because in the third equation, from the third equation, we know that the growth rate of the co-state variable is actually the negative of the interest rate. We can derive this from the third equation, and we can plug this result basically in here on the left hand side, and at the same time we then get rid of the co-state variable from this expression. So if we plug in here from this expression minus the interest rate, lambda does not appear anymore in this equation. And then we can reformulate it such that we put all the terms that are related to the derivatives of the utility function on the right hand side. And what we also do, that's just for convenience later on, we multiply by c over c here, this term, which does nothing actually to the term itself, because c over c is equal to 1, so it cancels out. But for the economic interpretation, what we can do now is we can isolate c dot over c, the consumption growth rate, and isolate it on the left hand side. So if we reformulate this expression here, we get the growth rate of consumption on the left hand side as a function of the interest rate and the rate of impatience, and a term that depends on the first and second derivative of the utility function and consumption itself. And as we will see in a second, this is again the consumption-Euler equation in the general terms, and if we use the particular utility function, the isoelastic utility function, we get to the familiar consumption-Euler equation, at least in terms of interpretation, because the interpretation is rather similar as compared to the discrete time case. This is now exactly what we see on the next slide, namely the isoelastic utility function that you are already familiar with by now. And now we calculate this expression from the denominator of the previous slide. So we take the second derivative of the utility function with respect to consumption. So 1 minus theta comes down, it cancels with this term drops out because it's a constant, and then we would have c to the power of minus theta minus 1. If we multiply it by c, we get c to the power of minus theta, and we get from the second derivative the minus theta also here. And if we divide this by c to the power of minus theta, the c to the power of minus theta drops out, and then the only thing that is left is actually minus theta here, and this with a minus sign, so the minus sign cancels out, and what remains is theta. So then we would have the consumption-Euler equation that we are familiar with. And again, theta is the inverse of the elasticity of intertemporal substitution, so it measures how willing people are to smooth consumption over time. The higher theta is, the less willing people are to depart from consumption smoothing. So the higher theta is, the lower is the elasticity of intertemporal substitution. If we plug this into the consumption-Euler equation from the slide before, so in this expression, so we have theta here, then we get the consumption-Euler equation in continuous time. And we are already quite familiar with this expression. On the left hand side we have the growth rate of consumption. Now it's the growth rate and not the growth factor. So if the growth rate is positive, consumption increases over time. If the growth rate is negative, consumption decreases over time. Now the consumption increase over time or decrease over time is a function of the interest rate, the rate of impatience, and again the coefficient of relative risk aversion in the utility function, which is the inverse of the elasticity of intertemporal substitution. Now again, if the financial market pays a high interest rate as compared to individual impatience, then the numerator would be positive. In this case, individuals would be induced to save because they are overcompensated for their impatience. But saving means nothing else than consuming less today and more in the future, so we would observe positive consumption growth. By contrast, if impatience of households is higher than what the financial market pays on savings, then the numerator would be negative and the growth rate of consumption would be negative. So people consume more today and less in the future, so we have this saving actually. And again, the theta moderates basically this, so the higher theta is, the larger the difference between the interest rate and the time preference rate has to be to induce a certain change in households' savings decision. Well, if the interest rate is exactly as high as the rate of impatience, then households would opt for a constant consumption path. Okay, again, as in discrete time, the growth rate is pinned down by this equation. So we have the general solution of this differential equation, but we do not have the particular solution. So the level of consumption is not pinned down by this solution. For this, we will need another condition, and we will come to this on the next. So now we've derived the solution of the dynamic optimization problem in terms of two dynamic equations. The consumption-Euler equation as the dynamic equation for the control variable, consumption, and the flow budget constraint as the dynamic equation for the state, the assets in our case. Now in general, one could derive the general solution of this system. And with two additional conditions, one could also derive the particular solution of this system. And the two additional conditions that we have in this case are the initial condition on the level of assets at the beginning, and we have the transversality condition stating that the limit as time goes to infinity of the product of assets with the discount factor has to be equal to 0. So we have an initial condition and an endpoint condition, and this in principle allows us to come up with the particular solution of the system of differential equations. However, as we will see, solving these systems of differential equations can be rather cumbersome and even impossible if they are non-linear. And in this case, we would have to resort to numerical solution methods or to linearizations, or, as we will do in the Ramsey-Katz-Koopmans framework, we have to resort to a qualitative analysis in terms of the phase diagram. And this is what we do next. So this slide now closes the part on differential equations, difference equations, and dynamic optimization in discrete and in continuous time. And we move on to have a look at one of the core workhorse models in modern macroeconomics, irrespective of whether we talk about growth theory or business cycle theory, namely the Ramsey-Katz-Koopmans model that you have at the core of almost all business cycle models, and basically also almost all growth models. And that's what we do next.